I'd like to discuss with you one more very instructive example of the asymptotic estimate of an integral. I hope that this exercise will help you to get more in-depth understanding of the steepest descent methods philosophy. And it will also help you with the more advanced exercises which await you around the corner as you progress with the course. So that's our integral in question. The task is to find the asymptotic estimate of this integral at large values of x, and x is assumed to be either positive or negative. The first thing you notice is that your exponent function doesn't contain large variable x in a homogeneous way, meaning that the exponent function can't be split into the product of our large parameter and additional function of t variable only. We've already encountered that kind of issue before, and the usual way to tackle it is to introduce some kind of clever rescaling of the integration variable, so the factorization is achieved. In this particular case, this rescaling is almost obvious. So why you introduce a new integration variable s, which is related to the old one by the following relation. And indeed, as you plug in this change into our exponent function, you achieve the desired factorization. And the integral is transformed accordingly. But sometimes that kind of rescaling may lead to potential complications. Indeed, let's have a closer look at our integrand. The initial integrand contains a simple pool and point -i, which is clearly independent of x. The transformed integrand contains the pool and point -i over x, which depends on x. For example, if x is positive, then the pole is positioned below the real axis of the s complex variable. When x is negative, the pole is shifted above the real axis. And for a second, the real axis coincides with the integration contour. So as x changes smoothly from positive to negative x, the pole, the singularity, crosses the integration contour, which is unacceptable. So that kind of complication which I was talking about. So sometimes when you make this rescaling, you have to be very careful, because right now, for example, it's not clear what's going to happen. You may probably need to bend the contour or something like this. So it all depends on the situation, and you have to adjust. The point is, however, that this requirement of the homogeneity of the exponent function with respect to a large parameter is mostly redundant in the steepest descent method, and can be safely avoided altogether. And the idea of this exercise is to show you how these two techniques, with rescaling and without rescaling, work and yield identical answers. And also, of course, the idea is to accentuate the differences between the two approaches and some subtleties. So let's first address the first technique without rescaling. So first, we consider the case of large and positive x. Let's find out the position of the saddle. And the stationary point equation is given by simple differentiation. So the saddle is positioned at point ix. And also, the contour is infinite. That means that its endpoints, the position of its endpoints has some freedom to move. But the motion is restricted to the region of the convergence of the integral. So let's discuss this convergence regions. So since we are interested in large T behavior, because obviously only large variable behavior is crucial for the convergence, we can simplify our exponent function. Namely, we can drop the linear in T term in comparison to the quadratic in T term, because the second one is going to be obviously the leading. So for large T, the exponent function is simply negative T squared over 2. So what would be the condition for convergence of the integral? Well, obviously, since this is an exponential function, we'd like this exponent thing to be large and negative. So in order to extract these regions, let's decompose our T complex variable into the modulus and the argument. So now our exponent function is as follows. And its real part. So the real part should be large and negative, meaning that the cosine of 2 phi should be positive, since rho is large. So we can solve this elementary trigonometric equation. And the solution single allows corner-like regions in a complex plane. And these corner-like regions are spanned by pi/4 angle in positive and negative directions. So here they are. Now let's figure out the steepest descent direction for our saddle. So to do so, we need to compute the second derivative, which is -1. And the steepest descent direction is defined by the argument of the second derivative. So it's the argument of the second derivative plus 2 alpha, where alpha is the steepest descent direction, must be equal to pi plus 2 pi n. Well, the argument is pi, so the steepest descent direction is simply pi n. So it's horizontal direction. So here is our saddle. Right. And this is the steepest descent direction. So now the correct deformation of the contour is more or less obvious. It's a simple parallel displacement of the contour upward in a complex plane by x. This way, it indeed will pass through the saddle in the steepest descent direction, and its infinite legs will be positioned in the regions of convergence of the initial integral.